Oh, you can hear me. Good morning. Good morning. Okay. Well, you don't have to applaud. I just thought you'd say good morning back to me. My name is Bill Venners, and this talk is kind of about faith. I have been thinking about how to make testing better for many years because we do Scala Test at our team, and that led me towards proofs. And so today, my talk kind of builds on a couple other talks that I gave in the last few years. So I'd like to start out by kind of refreshing, going back to a couple things I talked about in the past. 2 years ago at Scala Days, I had a talk called The Essence of Testing. And what I did in that talk this is a very short version of it. I showed this slide. This is a page of Eiffel code. Eiffel is a language created by Bertrand Meyer, who was French, still is French, and he named his language after the Eiffel Tower. And he had an idea in there called design by contract. That was what he called this idea of using assertions to specify the behavior of functions, behavior of your software. So what you do in Eiffel, this is a square root function in Eiffel, is I can't just to write square root, implement the algorithm to compute the square root. I also have to specify the behavior of this this function, which he called the contract. And it's kind of like what the service provider promises and what the person using it promises. He kind of captures that in assertions. So there's three parts to a function in Eiffel. You have the require clause, which is what he called preconditions. That's basically he had three kinds of assertions: preconditions, postconditions, and invariants. So here what I'm saying is that square root is actually a partial function because it's not defined on negative real numbers. So it's only defined on some of its input values, not all of them. So what will happen is that if a negative number is passed to square root, this will throw assertion error, essentially, at runtime, right? But what you're doing here is also specifying that the client, and this is the responsibility of the client in the design by contract worldview, the responsibility to pass in only positive or zero, positive reals or zero, is the responsibility of the programmers who are calling square root, right? And if they fail to do that, that's a bug, and they are punished. We are punished by getting an exception, right? Assertion error. Okay, then do is where you do the algorithm, and actually compute the square root. Ensure is called the postcondition. That's another assertion. So what that is capturing is what is the person who implements this algorithm promising, right? So what this one does is there's magically in Eiffel something called result, and that is the result that's about to be returned from the square root function that was computed by the do part. And so we square that, and basically this is supposed to be the square root of x, right? So if you square the square root of x in the mathematical world, it would just be x, you know. But in the world of floating point math, so this is like float or double in Scala, there may be some rounding differences, right? So what we do is we square the result that's about to be returned. You subtract the original x, and in the ideal world that would be 0, right? But there may be plus or minus a little bit, a rounding difference. And so we take the absolute value of that to make sure it's a positive difference, and then just make sure it's below a certain tolerance we're willing to accept for rounding, right? And that's the postcondition. So one of the ideas that he fleshed out in Eiffel is that assertions can be turned off at runtime in production because they actually take time to compute, and they're more about making sure you got your code right. So in develop and test, like if you have an SQA department that's just responsible for testing, in those scenarios you would enable all the assertions and they'd be checking all the time. It might be a little slower, but when you deploy to production you might turn these off. And he had a very fine-grained way of turning things on and off. You could turn on postconditions and preconditions and invariants separately, and actually just turn them on and off for one particular function if you want to in Eiffel. So that was his idea. And this didn't really win in the marketplace. What happened was that Eiffel kind of lost to C++. It was competing with C++ for mind share and sort of lost. And C++ didn't have this. And then Java came along. It also didn't have this. And then JUnit came along in test-driven development, and that really did succeed in the marketplace. So what we actually do on the JVM, not just in Scala, but also just generally on the JVM, is we do what's the default in Eiffel. The default in Eiffel is require, run are turned on, they're enabled, and ensure is disabled, right? So we'll do in, like if this is a square root function in Scala, I would normally have a require clause to capture my preconditions. And what this function does is if you've passed a negative number to math.square root, it will give you not a number. So here it will instead give you an exception, right? So that's sort of the value add, if you can call that value, getting an exception instead of not a number, over math.square root. That's what we're doing. So we say require that the number passed is not a number, it's greater than or equal to 0, and it's not positive infinity. If that's all cool, then we can call math.square root and return the result, right? And then we don't check the post condition. Now, yesterday Martin showed ensuring in the keynote, and ensuring is really sort of Scala's answer to ensure in Eiffel. So you can do design by contract in Scala also. And he showed that in Scala 3, with implicit function types, you can actually just say result, just like you could in Eiffel. So anyway, that's not common. He asked how many people use that, and I was in the front row, so either everybody behind me used it, and I just don't know. But I think most people don't use that, right? What we do is we take that post condition and we put it in this other place called the tests. Test-driven development was kind of like suggesting that you write a test first. So I might write this first assertion first. Square root of 0 should be 0. And then I go implement my square root function and just return 0. And now my test passes. Then I'll add another test, another assertion. Square root of 1 should equal 1. Now my test fails again. So I'll go actually implement my algorithm for square root, right? And what that doesn't do, though, is it doesn't capture the generality of what Bertrand Meyer had in Eiffel. If you look back here, what he's saying is really about all possible values of type real, all inhabitants of type real. For all reals, if x is greater than or equal to 0, then after the answer that comes back from this function should hold, the post condition should be true about. So this just says, well, 1 and 0 and maybe 42 or whatever I think are useful things to try. And this came to be called example-based testing after property-based testing came along. So what you can also do in Scala is use a property-based test where you get the sort of the same generality that you get with Eiffel, with defined by contract. I can say for all doubles, whenever, and then I just repeat the precondition, so I'm repeating myself. So I say it in the require, in the production code, and then I say it in the whenever, in this is like Scala test, property, and then I call square root and pass in x and I get a result, so that's where my result comes from, and then I do this sort of the post condition check. That's the post condition check. Same post condition check. So that's actually what happens to design by contract if you don't stick it in the code and you actually move it out to the outside, is you need a for all. And so that actually looks like predicate logic. So the talk I gave 2 years ago, the essence of testing, I said, well, this is actually what a test is, sort of by nature, it's a statement of logic, and the upside down A is for all. So for all x, P and Q are predicates. This predicate logic, you can have a predicate function that takes input and returns Boolean, right? So P, I've actually kind of said for my square root function, f is square root, that's the function I'm specifying. The type of x is double, so for all x, that actually means for all inhabitants of double, and that includes not a number, because that's an inhabitant of double. So def p double, it takes a double, returns Boolean, it just has that precondition, and it's true or false, right? That's the precondition. So if that's true, that little arrow there means implies, and that means sort of if then, right? So if the predicate holds, then the postcondition should hold. If the precondition is true, then the postcondition must be true. And the postcondition is a predicate function that works off of the input, like x, and the result, f of x. So in our case, I'm going to pass in the x and result, and I do my postcondition. That's the same postcondition math. So that was the essence of testing, is that you could specify a function on the outside with a statement of logic. When you specify it on the inside, it looks like design by contract. Okay, so that was that talk. And then a year ago or two years ago, I gave a talk called Hope, Faith, and Proof. which is mostly about where to use assertions in production code. And one of the places I suggested that we do use assertions and that it makes sense is require clauses, which are precondition checks. And the reason is that if something really is partial, square root's a partial function, we want to actually capture that early. So, I mean, one thing using a require clause does is it makes it really obvious that this is that this has this precondition. It kind of says that very clearly in the code. But also at runtime, you don't ever want that to actually happen in production, but if it does, you want it to happen as soon as possible, as soon as you can detect it. So you don't want to like just not check it and then go much farther and save some corrupt data to the database before you notice there's a problem, right? So anyway, the other idea that I kind of had in that talk was that if you have a require, it's good to do them if you have a partial function, but every time you do them, you should think, well, can I get rid of this by moving it into the type? So if I actually had a type that promised it's not a number, it's greater than or equal to 0, and it's not positive affinity, then I could get rid of the require clause, so that looks like this. So I actually could go to the shelf and pull off a positive or 0 finite double type. Then I could get rid of the require clause, and what I did is I removed one place that this could blow up in production. And I called this an expression of hope, because I hope no one ever passes, -3 to this, but I have no evidence that they won't, right? When I do this, the problem with it is I've just moved the problem to the call sites, because if somebody wants to call square root and they have a double in hand, they're going to have to convert it to this thing, and that could involve blowing up with an exception, right, if it's negative. But what I think is usually the case at the call site is you have nearby evidence that it will always succeed. So the other kind of assertion that I suggested it's good to use in production code is a kind where you make an assertion with nearby evidence that it will always succeed, you believe it will always succeed, and you move it to the type. So this would like move this knowledge that this is true about this value to the type and capture the type, and then I never have to check it again. And what that illustrates is that we trust types to fulfill their contract. So just if you pass me an int, I never do an assertion. Is the value greater than or equal to min int and less than or equal to max int? I just trust that, right? Because if I didn't trust types to implement their contract or to fulfill their promises, I'd have to put all kinds of assertions all over the place. So that's where we hang our belief on. We believe that types are going to fulfill their contract, and we pretend, even though we know there are bugs out there and sometimes they won't fulfill their contracts, the way we program is that we trust them. Okay. So that's essentially the two things from past talks I wanted to kind of start with, because this talk builds on top of them. The first one is that's sort of the nature of how you would specify a function, f of x, is a little statement of predicate logic. And then we trust types to correctly implement their contracts in practice when we program, when we write code. Okay, so now to the new stuff. For this, I'm going to use natural number as an example. And this is also kind of like if-then. If the thing on top of the line is true, then the thing on the bottom of the line is true. So what a natural number is well, in computer science, we usually start with 0. 0, 1, 2, 3, 4, 5, 6, 7, ... right? So it's actually an infinite set of numbers. It never ends, right? So what this is a way this is using induction to define an infinite set with a very finite set of rules, right? So the first rule is the base case, and that is sort of like, we don't have any precondition that has to be true before on top. There's nothing up there, so that's kind of like true. So there's just a 0. We're just going to declare 0 as a natural number. That's kind of like, let there be 0. And then the second rule here is the inductive rule, which says, if P is a natural number, then the successor to P is a natural number. And I picked P because that stands for predecessor. On the 0th day, when you wake up, you can get 0 because that's free. It's just 0 exists, right? Let there be 0. On day 1, the next day, I can say, well, 0 is a natural number, well, therefore the successor to 0 is a natural number, and I get 1, right? And then on day 2, I've got 0 and 1, so I can say, well, 1 is a natural number, therefore the successor to 1 is a natural number, and that's 2, right? So that sort of is how you define, with induction, an infinite data type. And in Scala, you could do it this way. I say seal trait nat, case object 0 extends nat, and case class suck. It takes a predicate, a predecessor, which is a natural number, right? P is a subtype of nat. And that's my two cases, and I can just demo that real quick. Okay, go over to this guy. Just paste that in there. So I could say val 0 with a little z is 0, val 1. So this is, now that I have 0, I can use the other rule, the inductive rule, and say 1 is the successor to 0. I can say 2 is the successor to 1, right? And then I could keep going, but I only have 40 minutes for this talk. But it goes forever, right? So what you'll see here, the way I wrote this, it does capture in the type what the number is too. And in the toString, you can see the nesting of these suck classes. And you can just count them. So, this is a 1 because it has one suck constructor invitation. There's 2 sucks here, and that's 2, right? And there's 0 sucks here, so that's 0. Okay, so that's that guy. And then now I want to add a method to it. I want to add to add 2 natural numbers. So I define just an abstract method in my sealed trait nat that is plus, takes a nat and returns a nat. And then in my 0 case, I just return the right-hand side. So I called it R because that's the right-hand side. And adding anything to 0 is that, whatever you added to 0. So that's that one. And then over in the successor case, what I do is basically the call site. You have successor of P plus 1. So let's say P is 3 plus 1. So the successor to 3 is 4 plus 1 is 5, right? So what I do here is I say, well, if you just add 4 plus 1, the successor to 3, P is 3, 3 plus 1, that gives me 4, and then I take the successor of that gives me 5, that's the same thing. And what I'm doing is I'm calling myself recursively with 1 less than this. So it will eventually hit the 0 case, which doesn't recurse anymore. So I can demo that, just so you believe that it actually does add. So I'm going to have to do my little inventing. I better not try to talk while I'm doing this. Equals successor of 1. That would loop forever. And then I'll just make a 3 for the heck of it. 3 equals successor of 2. So you get the idea. So if I say, for example, 0 plus 1, I get 1. There's 1 suck there. 0 plus 3, I should get 3 sucks. Yep, that's 3. If I say 2 plus 3, I should get 5. So I'm going to count them. Here's 1, 2, 3, 4, 5. Right? So that's addition. Okay. So open that up. So that was addition. And now what I want to do is write a test. I didn't write a test first. So I want to write a test second. And I want to say that my plus method is going to promise that it will be associative, right? So when I say, basically, if I have 3 natural numbers, A, B, and C, A plus B plus C equals A plus B plus C, right? So I could do a few example-based tests like this. 1 plus 2 plus 3 must equal 1 plus 2 plus 3, right? And then I have another one, and so on, right? So that's an example-based test, but you could also do the for all thing. I mean, essentially, it doesn't capture this notion of that it's for all natural numbers A, B, C. I want this to be associative. So I could do a for all like this. I just say for all natural numbers A, B, and C, A plus B plus C must equal A plus B plus C. That's kind of hard to say. But so I'll show you that. I got that over here. Essentially, here's a natural number that's just like I had on the slide there. And then in this, to use a property-based test, the one other thing I need is I need a generator for natural numbers. And so here I just took an int generator and said from 0 and 100 because these things actually do take up memory. I probably in production would use a larger one, but you don't want to have it like 0 to a billion because you might run out of memory. So let's just say 0 to 100, and I just have a toNat method that's recursively, takes an int and turns it into a natural number. And then down here, I just say for all natural numbers a, b, and c, and there's my little assertion. So I can actually just exit here and just run the test, and you will see it passes. All right. So what I also wrote here, just to kind of let you see what's going on, is I wrote a little function called toInt that put inside here. ToInt will take a natural number and return it. It goes the other direction as my little toNat up here. And it's a little recursive, tail recursive loop. And so what I'm going to do now is for each one of these tests that we test, I'm going to print it out so you can see what's printing. So you'll see the integer version of it, and then you'll see the actual natural number version of it here. So now when I run my test, you'll see a bunch of print statements. And then this is Scala test generator that'll be out in 3.1, and we do 20% edge cases combination. So here's 100, 101. So there's like, what's the next one? 1, 0, 100. So here's 1, here's 0, and this is what 100 looks like. And it thinks 100 is an edge case because I use ints between 0 and 100. Then we just kind of randomly all over the place try stuff. But one of the things I didn't try is 101, right? Because I'm only going 0 to 100. So even though this looks like predicate logic, this for all, it actually doesn't. It's still example-based testing in a sense, because I'm just trying different things. So what I had this slide also in my Hope, Faith, and Proof talk, and it's called Maybe Einstein, because Einstein is often quoted as saying this, but there was actually no evidence after the fact that he said it, so maybe he didn't say it. But what the quote is that no amount of experimentation can ever prove me right. A single experiment can prove me wrong. And so like the theory of relativity, because it's like a theory, it's a mathematical model of reality. So the scientific method says we don't just take that on faith, we try it. We do experiments to see if it actually holds. And no matter how many of those experiments you do, that's not a proof that it's correct. Someday, like tomorrow, there could be an experiment that actually shows there's a problem with it and it needs to be updated, right? So that's kind of what we do with software development today when we write tests, is we're doing science. We're saying, well, I'm not going to have faith that my thing works, even though, maybe I think it looks like it should work. I'm going to test it and make sure, right? And those tests, even if it's a for all, because we're just trying certain values, doesn't prove that it works, right? It just makes me more confident that it works. But if you have a test that fails, that's pretty close to a proof that there's a problem. Either there's a bug in my algorithm, or there's a bug in my test, or there's a misunderstanding, so there's a bug in our communication, or there could be a bug in the hardware, who knows? But there's a problem. Okay, so what you can do in programming is you actually can do better, because programming, at least the functional part of your code, is like can be treated mathematically, and then you can do proofs. So what I'm going to do is I'm going to prove 1 plus 2 plus 3 equals 1 plus 2 plus 3, right? So what I'll do is I'll start with the left-hand side of that equality. And then I can say, well, 1 plus 2 is 3. 3 plus 3 is 6. Well, 6 is 1 plus 5, right? And 5 is 2 plus 3. And what I did is I started on the left-hand side, and I ended up on the right-hand side. So that's my proof. So when you see mathematicians doing proofs, they either end it with a QED or this little square, which is pronounced voila. It means, here's my proof, right? So I just did it. So I could do that again with this other example, but this is kind of like example-based proof, right? What I haven't done is I haven't said that, I've proven that for all natural numbers A, B, and C, associative, addition is associative, right? So to do that, so that's what I'm going to try to do now. And what I'm going to do is I'm going to pull some sort of mathematical equalities out of my code. So for the 0 case, what I can say is that 0 plus r equals r, because if a client says 0 plus r, what executes is it returns r. So you can kind of like see the left side of the equal sign is the client code, the right side of the equal sign is the body, right? And then for the successor case, the left side of the equal sign here is sort of the client code again. Successor of p plus r, that will invoke this function. And that kind of substitutes the right-hand side expression, which is the body, right? Successor of p plus r in parentheses. So now I basically want to prove, my for all ABC, addition is associative for all natural numbers. And I know these things. And I also am going to allow myself to add or remove parentheses, okay? So, because, one way to do this is just enumerate them, right? I say 1 plus 2 plus 3 equals 1 plus 2 plus 3. I just proved that, so I could say, well, 1 plus 2 plus 4 equals 1 plus 2 plus 4, right? But of course, again, it's infinite, so that you can never enumerate all of them. So I'm going to prove by induction, which kind of mirrors the way I defined the data type in the first place. So I'm going to prove basically I'm going to substitute A for either 0 or successor of P. So in the 0 case, I'm going to basically A plus B plus C becomes 0 plus B plus C, and that equals 0 plus, and then in parens B plus C. And that one I'm just going to prove like I did 1, 2, 3, right? Just prove it outright. But then the rest of it I'll use an inductive kind of proof where I say, well, if P plus B plus C equals P plus B plus C, that's my precondition. If that's true, then successor of P plus B in parens plus C equals successor of P plus B plus C, and that's sort of my, I have to prove that. And what my claim is that if I prove both of these, then that proves that my addition is associative, my addition method. Okay, so because we're programmers, because I'm a programmer, I think of this as a algorithm. So given an A, if A is a 0, you could say A match, case 0, right? If it's a 0, then I need to prove this for all BC, 0 plus B plus C equals 0 plus B plus C, right? Otherwise, since A isn't 0, that means it has to be a successor, and there's a P in there. So I would need to prove for all PBC, and there's my if-then, right? There's the top and the bottom of that rule. If P plus B in parens plus C equals P plus B plus C, right? If that's true, then I need to prove this bottom line, right? Okay, so that's my algorithm. So let's do the 0 case first. So I'm going to start with the left-hand side. So basically A is 0 now. And so that means that the left-hand side of my equation is 0 plus B in parens plus C. So the first rewrite I can do is, because I know 0 plus R equals R, I can get rid of the 0 plus there. Right? In other words, I have one of these equations, 0 plus R equals R. That's actually from my code that I'm trying to prove is correct. So I can use it to do a substitution, and then I can get rid of the parentheses because I'm allowed to do that, and then I can actually add a different set of parentheses because I'm allowed to do that, right? And now I can go back to my rule, but go from right to left. So B plus C in parentheses you can see as R on the right-hand side. So I can stick a 0 plus in front of it, right? And now I've basically ended up with the right-hand side of my equality. This is just kind of like the way I prove 1, 2, 3. I got to, basically I just proved that base case. So that's that one. And so now the more tricky one is this guy. So I'm going to start with the left-hand side again. And it's essentially, over here I substituted 0 for A at the top line there, 0 plus B plus C. That's one case. The other case is I'm substituting successor of P for A. So that's why I start with that. So successor of P plus B in parens plus C. That's what I start with. So now what I can do is, inside the parens there, I have the left-hand side, I have the shape successor of Y plus R, except, Y is P and R is B. So I can actually change it to the right-hand side. So now inside the outer parens there, it's successor of P plus B. That's actually from my code. That's what my code's going to do. And then I can get rid of those extra parens that I don't need anymore for that same rule of being able to add and remove parentheses. And now I'm going to use this rule again. It's the same, like it has that left-hand shape again, where y is now p plus b, and r is c, so I can make it look like the right-hand side. Again, this is like referring to my code. This is what my code's going to do. The successor of, now I have successor of p plus b plus c. So now I'm stuck. So I'm going to do something kind of iffy here. And I'm actually going to call the proof that I'm using. I'm going to actually use the proof that I haven't finished yet in the hope that I will be able to finish it. So if you look at the inside of the parentheses, so it says successor, parens, so look what's inside there. It's in parens p plus b, then plus c, right? And if you look up on top, that's the shape of the left-hand side, right? That's actually the shape of the left-hand side. And it's also the shape of, like, if you look at the first line there, successor of p plus b plus c, right? It's the same shape. So this proof, what I'm trying to prove is this is associative, and if I actually succeed, then I'll be able to actually change that to that. That's what I'm trying to prove. So I'm actually going to call this proof recursively, if you think of it as an algorithm. And, but I'm going to replace successor of p by p. So if you look at the first line, it says successor of p plus b in parens plus c. And now here, the second to bottom line, it says p plus b plus c. So here it's actually one smaller. And so the reason I believe I can do this is because I went one smaller, and even if I start out at a quintillion, eventually, like, this will recurse and get all the way to 0, which doesn't recurse, right? So anyway, as long as I'm able to finish my proof, this should be okay. And now the last thing I need to do, there's just one more step though, is I can do one of these rewrites again. So this one is basically the second to last line. Let me just back up one. This line looks like the right-hand side now. So what I can do is I can pull the successor out, and so it's successor of p out plus b plus b, and that's actually what I was trying to get at. And that proves the successor. So that's sort of like the feel of how you do proofs. And what I did is I sort of took my code and pulled it out into sort of these little mathematical statements, and then I could do a proof with that. Okay. And it's hard. So there's been a lot of research in recent years in the functional programming world about doing proofs, like using a dependently typed language. So what I want to show you is what this looks like in Ogda. Ogda is a fully dependently typed language, which means the terms can show up in types. You can index a type by a term. And so what I would have to do this proof in Ogda is sort of like emulate my Scala code. So I've got an ADT there that sort of has the same shape as my natural number. And I didn't show the addition method. But what I have down here at the bottom is, like, you can think of ASOC as a val and colon, and then to the right of that is its type. And it's a function type. The arrow there is like a function arrow. So it's like a val that refers to a function. And it takes 3 natural numbers. For all is kind of like syntax sugar. It takes 3 natural numbers. And what it produces is evidence that a plus b in parens plus c will always be equal to a plus b plus c in parens. So it doesn't compute. It computes something of that type. And so what these dependently typed languages like Idris and Ogda do is they use the Curry-Howard isomorphism to say that propositions are the same thing as types, or like they correspond to types, and programs correspond to proofs. So if you actually can, you can describe a proposition in a type, and then if you can actually get your program to compile, get an inhabitant, like actually implement that, initialize that a value of that type, that actually is a proof that that proposition is true. So that looks like this. This is actually the same algorithm I just went through on, well, not on paper, but on slides. This is how you would do it in Ogda. This came from Phil Wadler. Phil Wadler has a programming language foundations in Ogda book. So this came from there. But this is how it will look. So you can actually do it mechanically, and it's like programming. So instead of writing tests, which is like programming, you would write proofs, which is like programming sometimes. Okay. So anyway, that's what Agda looks like. And so the description of this talk, I talked about like using statements of predicate logic to define contracts. So going back to Bertrand Meyer, he said, let's define contracts formally with assertions. And what I'm suggesting, and I kind of wanted to like propose this as an idea, and actually I'll be here. The nice thing about having my talk be first is you guys can come up and talk to me and tell me what you think. I was kind of curious what you think of this idea, that we would, as programmers, actually do the kind of the more formal specification of the contract, but it would not be assertions. It would be statements of logic. So like I might say for my plus method on NAT, 0 plus R is R plus 0 is R. That's like left identity, right identity. This is like the body of my successor method. I could say that's going to always be true. And then I have, for all ABC, A plus B plus C equals A plus B plus C. That's associative. Then I have commutative, and I may have other things, right? And that's my more formal specification of the contract. Usually what we do on the Java platform is we write it in English for the most part. We say what this thing does. Because if you do this, then you can either use property-based tests or proofs to sort of give yourself confidence that you are meeting your promise. And essentially, I'm promising all those things as the implementer of NAT. And proofs are really hard. So maybe I don't have time or whatever, so I can use a test. And I think that's fine because we have faith in types, right? But this would allow us to, it sort of gives an extra tool. Like if we could add like in addition to a test framework, you had a nice proof framework that sometimes you could use where it made sense, then you'd have actually, it'd be better than testing. It would be better than science, right? It would be mathematical proofs. So anyway, the other idea that I wanted to sort of throw out there is that because we trust types, we should be able to use the contract, which is like these statements of logic, of any of the involved types that we use as axioms. So we don't have to, we can just trust that they are fulfilling their contract, whether they had proofs or not. If they're just tested, I mean, I don't think I don't know that there's any proofs for int on the JVM that it fulfills its contract. But I trust that it's going to be between, min-int and max-int. And that's fine. But, so I can actually use the, for my toInt method that I showed you that sort of did the output in the test, one of the things that would have to do is, this is a partial function because it's not going to work for any int greater than max-int, right? So that would be my precondition, sort of like the px. And then I'd have to somehow express that, if you count the nested levels or something, then you'd get the output, right? In a proof of that, I could use all these guys, for example, because I trust NAT to fulfill its contract. And I would not actually use the code, even though like here, sort of this was based on the code. I could refactor that code, and I'd need to make sure that still is true, even if I'm using a more efficient algorithm than successor of P plus R or something. I need to be, like the other proofs need to depend on the interface, not the implementation of the code. So anyway, that's the idea. So, I kind of was thinking they're like unit tests. Unit tests just look at one thing. So unit proofs is not trying to prove everything works. I don't have to prove nat and int work just to prove my toInt works. I just assume all that other stuff works. I take that as an axiom, and then really what my proof says is so long as nat and int fulfill their contract, then toInt, I've proven that it fulfills its contract. So that's I call the unit proof. So anyway, that is my talk. So before I go to questions, I just wanted to mention that we are hiring at our team. We do consulting. We are available if you need help. And then I'm also a member of the advisory board of the Scala Center, so I actually represent the community. So if you have any concern, please come up to me at the conference. I look like this. And I also do these brown bags. So if your company would like me to come in, like probably over video or whatever, it's kind of like a psychiatry session. You get on the couch and I show you ink blots and I say, if this is Scala, what do you see? And you tell me like what your concerns are and what you like, what you don't like, and I can kind of bring that back to the Scala Center. So anyway, are there any questions? I have like a few minutes for questions. Yeah, he's going to bring around the microphone if somebody has a question.
Thank you for your talk.
Oh, you're welcome. Where are you? Oh, there you are. Hi.
I did maths at university, and I'm a little bit uncomfortable because it's not really for all numbers, because computers are limited. How would you manage that?
Oh. Well, I think what you're saying is that if I do this proof here, for example, this guy, it's not, even if I go back to this, let's say go back to this guy. If I prove this, it actually, I think it's okay, because what you're saying is computers actually can't get up to a quintillion because it won't fit in memory. But all the ones it can get to are, I've proven that is correct. All the ones the computer could actually fit in memory. And that's better than testing, is my point. So I think, that it's like proof in the mathematical sense isn't proof, or like especially a unit proof. It's not proof, absolute proof beyond all reason, absolute proof beyond any doubt. It isn't. But it's still useful. It's like if, it's kind of like an axiom. If everything fits in memory and, natural number and int fulfill their contract, then my 2int method, this guy, fulfills its contract. That's all I'm proving. It's like a unit proof, and that's good enough, I think. That's, yeah. Does anybody have another question? So people are spread out, way back in the back, yes.
Hi, thank you for your talk. It was great.
Thank you.
Most of the assertions you did was using proofs by induction.
Yeah.
And in maths, there are different type of proofs, including proof by contradiction or otherwise. Have you considered any of that?
Yeah, I mean, if you look up proofs for associativity, there's a bunch of different ways to do it. So what I wanted to do was basically I want to do programming, right? So I want to use one of these dependently typed language. You can think of like Ogda as a proof framework for Scala that you have to, it's not very integrated. And that's one of the things Ogda does, is that kind of recursion. But yeah, this is as far as I got, is just sort of kind of figuring out that this is sort of like, I think that just makes sense. I just think it'd be nice to have a more formal specification of contracts. And it ended up looking like logic, which perfectly matched, property-based tests looked exactly like that, but so do proofs. So that's how to actually do proofs is I don't know. I haven't done too much with that. And I just think what I would have observed is it's really hard to do proofs. I think it's kind of fun. It's like solving puzzles, but it's not like, you can write a test, but you can't necessarily do a proof. So, anybody else? Anybody else? Going once. I may not be seeing a hand. Okay, cool. Well, thank you.